So we are looking at radioactive decay today, and this falls under the category of nuclear change. So remember, in chemistry, we're looking at matter and how it changes, and we are specifically thinking about nuclear change right now. If you want a broad review of everything on this slide, there's a separate video for that. So we're just going to jump right in. So remember that when we're talking about nuclear change, we are talking about, for the most part, isotopes that are unstable. And for radioactive decay, it's all about how those unstable isotopes are ultimately spontaneously falling apart, related to what they have going on with their ratio of protons to neutrons and their strong nuclear force. This slide is also covered in another lecture, so it's just a little intro review. Okay, here's our first new slide. So again, when we're thinking about nuclear change, we have atoms of one element changing into atoms of a different element, and that does not happen in chemical or physical changes, but in nuclear changes, it does happen. This can occur through fission, fusion, or radioactive decay. And all of these processes release energy due to changes to the ratio of protons and neutrons in the nucleus and what's going on with the strong nuclear force. So there was a separate lecture that looked at fission and fusion. This one, we are looking at radioactive decay. So radioactive decay is the process of unstable isotopes spontaneously falling apart. That's different than fission or fusion, which had other things initiating those. This is just happening kind of on its own timeline. There are three main types of radioactive decay: alpha decay, beta decay, and gamma decay. And all of these types of decay have something being released. So when we hear this term radiation, it's referring to these small, fast emissions that are coming off of atoms undergoing decay. And then those emissions oftentimes will go somewhere and interact with something. So when you hear the word radiation, it's probably related to these different types of decay. So I'm going to zoom in on all of them. This is just an overview slide, so we will continue our journey. Before we look at each type, I want to connect it back to our band of stability, which, remember, our band of stability shows us the different types of isotopes. What we are looking at today are the unstable isotopes, because those are the ones that are going to undergo radioactive decay. We looked at this cloud chamber lab, and the purpose for that was just so we could understand that decay is something that can be observed. The things that are emitted from the radioactive isotope, we can actually observe them. So you have different patterns coming off here, and that's because they are actually different types of decay happening. So on the previous slide, we saw how alpha, beta, and gamma decay are the main ones. Here, this graph is just to kind of give you a sense of like which elements are going to undergo which types of decay. So for your alpha decay, those are going to be your heavier elements, and we'll talk about why a bit later. So things that have an atomic number like over 82 oftentimes will go through alpha decay. Beta decay, usually it's going to be like they have too many neutrons. And so here, again, if you have neutrons here, you can see that unstable isotopes that fall more on this side of your band of stability are going to have a higher number of neutrons in their proton to neutron ratio. And then gamma decay kind of actually will happen oftentimes at the same time as alpha or beta decay. So all of these slides are just to kind of give you some grounding, foundation, like bigger picture understanding of decay and why it's going to happen. So we are now going to zoom in to our different types. So we have alpha, beta, and gamma. And then here's our picture here that's going to kind of compare them. So first is alpha decay. It usually happens with those heavier elements, and what's going to happen is alpha particles are released. So here is your parent atom, which is going to be an unstable isotope. And then this little shaded thing here is actually what we call an alpha particle. So an alpha particle has 2 protons and 2 neutrons, and because of that, we often will call it a helium nucleus, because if you look at the periodic table, helium has 2 protons and 2 neutrons. So alpha particle or helium nucleus. Basically, in alpha decay, that alpha particle will spontaneously be released from your parent atom, and the daughter atom then is a more stable atom, and it has 2 fewer protons and 2 fewer neutrons than the parent, so it's actually become a different element, which, remember, nuclear change is all about atoms changing their element. We can model it with a nuclear equation. You have your, for example, uranium-235 going through alpha decay. Here is the alpha helium particle that has been released, and then your resulting daughter atom. When you are doing these equations, the way to determine what the daughter is going to be is to look at your periodic table and move to the left by 2, because you want your atomic number to be 2 less. Again, you can track your law of conservation of mass here at the bottom if you want to pause. So that's alpha decay. It generally is going to be happening with those heavier elements, because you can see helium is relatively massive. There's a good amount of mass there, so it's going to lose some mass, and in the process, it will then become more stable. So here is alpha particle here. All right, moving on to beta decay. For beta decay, you actually have a neutron turning into a proton, which I know that sounds probably pretty whack, but that is what happens. So you have your unstable isotope, the neutron turns into a proton, and in the process of that, you have an electron and an antineutrino released. So this electron here is actually what we call a beta particle. Don't try and worry too much about the mechanism of what's going on here. That is way beyond the scope of this class. You can focus on the phenomenon and that, like, this is what happens, and don't worry about the how, because that's a deep nuclear physics answer. Again, you have a nuclear equation. So you can see your proton is actually going up, and you started with 6 protons and 8 neutrons. One of those neutrons turns into a proton, giving you now 7 protons and 1 less neutron, 7 neutrons. So the daughter atom is actually going to have 1 more proton. So it's going to be to the right on the periodic table by 1. Since the neutron turned into the proton, the number of overall protons and neutrons is going to stay the same, and it will have the same mass. Again, your electron is the beta particle. So we show that in the equation like this. It might seem a little weird to have a negative one here. Mostly it's because that's just the notation that we use, and you can see this notation allows everything to still be balanced because you have a 7 minus a 1. An electron is also like kind of the opposite of a proton. Don't overthink it. It's notation. Here's our last one, gamma decay. So for gamma decay, it's not actually a particle that gets released, it is energy. And what happens is the nucleus of your parent atom is in this really excited high energy state. And similar to when we talked about electrons being in high energy state, in order for them to move to a lower energy ground state, they need to release a photon. They need to release energy. So that's exactly what's going on with gamma decay, is that there is an energy release that occurs, and then that nucleus moves to a lower energy state, which is going to be more stable. So in gamma decay, the daughter atom actually is the same element, but it's a more stable version. Oftentimes, gamma decay will occur alongside alpha or beta decay, which is what you see in these nuclear equations. So the change in element, like if you were to just look at this part of the equation, it would just be a normal alpha decay equation. Same thing with this one. If you just look at this part, it's just a normal beta decay equation. So you can see adding the gamma on to the end here, it doesn't affect the identity. It doesn't affect the number of neutrons or protons. It's just showing you that gamma is also getting released. So we want to look at this little picture real quick to just kind of compare the different types of radiation that are being emitted from the different types of decay. So alpha decay releases an alpha particle, beta decay releases a beta particle, and gamma decay releases gamma rays. So you can see this is not a particle, it's represented as waves because it's energy. So alpha particles are bigger, and so they get stopped by something even like paper will stop an alpha particle. Beta particles can move through paper, but something like aluminum will stop them. Gamma can penetrate through a lot of materials. And so because of this, it is the most dangerous form of radiation. Okay, so here's just our kind of like zooming back out. So again, you can see these little pictures kind of showing like here's alpha decay, an alpha particle has been lost, and so this nucleus is now like missing something. In beta decay, what's really happening is an electron is leaving and then a neutron turns into a proton, so your nucleus is a little bit changed. And in gamma decay, you've got energy being released and the nucleus is the same. This is kind of your like overview slide for what you want to get out of this idea of radioactive decay. Ultimately, radioactive decay is something that is occurring naturally because you have these radioactive isotopes that are not stable, and so therefore they're going to fall apart. And there's 3 different ways that they can fall apart. And then all of those ways have this like, there's something that's getting radiated out that is small and fast and traveling. So that might bring up the question, okay, well, how long can something be radioactive? Like if this is just something that happens spontaneously, what's the timeline? So radioactive decay happens at a constant rate, and we call that the half-life. So the half-life is the amount of time for half of a sample of a radioactive isotope to decay and become a new element. So that's shown here in the graph. So here, like this would be 1 half-life, if you have number of half-lives on your x-axis, and percentage remaining on your Y. Once one half-life has gone by, that length of time, you now have 50% of the isotope remaining. The other 50% has turned into another element based off of whatever type of radioactive decay it's going through. After 2 half-lives, you then have half of your half, and so on. Every element has a different half-life, and those can range from like a fraction of a second. It can happen really, really fast, or all the way to billions of years. Each element is different. Half-life, this is why nuclear waste is radioactive for so long, because those products of nuclear waste that you get from fission or fusion, most likely fission, those products then go through radioactive decay and they have really long half-lives. So they are emitting these alpha or beta or gamma rays for a really long time, which makes them dangerous for a very long time. Another time you may have heard of half-life is if you've ever learned about carbon-14 dating. That's where half-life, that idea is utilized for determining the age of an old dead organic object. If you want to learn more about that, you can look it up, but it's just a tie-in. Okay, so this lecture I think is kind of hard because it goes into these really deep topics, but it's actually like a pretty surface level look at them. So what I wanted to do to wrap this lecture up was to try to clear up a little bit of that, make some connections to your everyday life, and just kind of